This is lesson 30. Everyone.
Okay.
That's it.
Yes, this is lesson 30. All right. It's very, very short. But let me just kind of introduce where we're going with this, okay? We want to focus on those points that we found in the previous lesson, or that we recognized in the previous lesson. We didn't really have a name for them at that point, but it was the name of the point where we changed from being concave up to being concave down, or from concave down to concave up. Those points have names.
Wait, I thought it's the relative max or min.
That's where the first derivative changes from positive to negative or negative to positive. That's the relative max or min. This is where the second derivative changes. We have another name for those points. Okay? And that, I'll just tell you, the name of those points is called the point of inflection. You can see the term right down here, the point of inflection. Okay? Now, you can see kind of a picture down here before we do this example. You can see a picture here where we have a point where it changes from being concave up to being concave down. Okay? And it's kind of interesting, you know how we said that some points, like the plateau points we saw before, the tangent line actually goes through the graph? Well, that's because the plateau point is an example of a point of inflection. Plateau points are critical numbers and they're points of inflection. And the tangent line actually goes through it. Okay? And we change concavity at that point. This can also occur, like we said, when the derivative is undefined. Okay? If the derivative is undefined, we have a vertical tangent line that curves up and then goes like that. Okay? So we can illustrate that here with this function real quick. This is just a polynomial, so we'll run through the derivatives real fast. F prime is 4x cubed minus 12x squared, and f double prime of x is 12x squared minus 24x. Okay? And if I factor that, that's going to be a 12x times x minus 2. Okay? 12x times x minus 2. So, where is the second derivative equal to 0?
2.
At 2 and?
0.
Okay. So f double prime equals 0 at x equals 0 and 2. So what I'm going to do over here on the table, here's 0 and here's 2. So the intervals that I have are x is less than 0, x is between 0 and 2, and x is greater than 2. Okay? And now we can simply plug in values in each of those intervals. Okay? Now notice, what am I plugging them in, these values into? The original function, derivative, second derivative. I'm trying to determine concavity.
Oh, second?
So I'm going to plug it into the second derivative, okay? So, let's say we have a negative 1, we could use 1, and we could use 3. So if I plug a negative 1 in, I have negative 12 times a negative 3. So that turns out to be positive, which means I'm concave up. There we go. Okay? Then we plug a 1 in, and I have 12 times negative 1.
Down.
That's negative. So good. It's down. Concave down.
I'm getting it.
All right? Good, good.
But maybe not on
And then if I plug in 3, I have 36 times 1, which of course is positive, so it's concave. Up. Alright? So, guys, what this means here...
Is it always like up, down, up, down?
No.
It often is up, down. Okay? Kind of like, remember, increasing, decreasing. Most of the time it did kind of switch back and forth, increasing, decreasing. But always test it, just to make sure. Now, what this means then is we have points at 0 something and at 2 something, which if I plug it into the original equation, it's 0, 0, and 2, let's see, 16 minus 32 is a negative 16. These are points of inflection. They are points where we change concavity. Now we don't have like max and min where there's two different kinds. We just call them points of inflection. Okay? Alright, so this all brings us to the second derivative test. I know lesson 29 was called the second derivative test, but that was kind of the beginning of our progression towards this point right here. Okay? And one thing I want you to understand here is what the purpose of the second derivative test is. Okay? We've already looked at the fact that if you want to determine if something is a relative min or a relative max, you can use the first derivative, set it equal to 0, and find your critical numbers, or find out where it's undefined and get your critical numbers there too. But then you would set up the sign diagram, and anywhere you saw a change in direction from increasing to decreasing, you had a max point, or from decreasing to increasing, you had a min point. Okay? What the second derivative test does is it allows us to take those same critical numbers, but we're actually going to use the second derivative to tell whether they are max or min points. Okay? So we don't have to do the whole sign diagram, we just take the second derivative, and we're going to actually plug those values into the second derivative, and that'll tell us whether we have a max or a min point. Okay? So let's look at what this rule says. Here's the first part of it, and that is if the first derivative equals 0, in other words, we have a critical number, and f prime of c is f double prime, of c is greater than 0. So that means we are concave up. Then f of c is a relative minimum. Okay? So in other words, if we have a critical number here and it's concave up, that means we have a min point there. Okay? That's pretty simple. On the other hand, if the first derivative equals 0 and the second derivative is negative, which means we are concave down, then f of c is a relative maximum, and you can see that up here. Okay? So here is our critical number, and it is concave down. Remember, we can tell it's concave down because if we draw the tangent lines, they're all on top of the curve. Okay, that's the easy way to tell concave up or concave down. Then we have a maximum. Now, what if we try this and it fails? Okay, well, by failing, we mean, maybe it equals 0 at that point. Okay, so the first derivative equaled 0 and the second derivative equaled 0. We could then go back and use the first derivative test, where we're looking at increasing or decreasing. Okay? If the second derivative was undefined at that point for some reason, again, we could go back and use the first derivative test. Alright? So, again, this is just another way of determining max and min points, relative max and min points. Okay? Now, let's look at an example of this. I'm going to hide the graph, and we'll just look at this. It says, find the relative extrema for f of x equals negative 3x to the fifth plus 5x cubed. Okay? So, the first thing I'm going to do is I'm going to find the first derivative. F prime of x is a negative 15x to the fourth plus 15x squared. And now I'm going to find my critical numbers. All right, I know there's nothing that is going to make this undefined because I have a quartic polynomial there, and polynomials are defined for all real numbers. So I really only have to find the values that will make our first derivative equal to 0. Okay, so I'm going to factor this. I'm going to factor out a negative 15x squared, and that's going to give me an x squared minus 1 inside the parentheses. So what does x equal here?
0 and
There we go, 0 and plus or minus 1. Okay? So, that tells me there are 3 points that come as a result of having these 3 critical numbers. Okay? Now, to find the y-coordinates of these points, what am I going to plug the x values into? The original function, alright? So if I plug in a negative 1, I have a positive 3 minus 5, that's negative 2. If I plug in 0, I get 0. And if I plug in a 1, I have negative 3 plus 5, which is 2. So those are the 3 points I'm considering. Okay? And now we need to consider the sign of the second derivative. So now I'm going to take our second derivative. Notice here I'm not checking increasing or decreasing. I'm just going to look at the sign of our second derivative. So f double prime of x is a negative 60x cubed plus 30x. And now I'm going to plug in negative 1, 0, and 1. Okay, so f double prime of negative 1 is going to be a positive 60 minus 30, which is 30. So that's positive. So what does that tell me about the point negative 1, negative 2? It's a minimum point, okay? It tells me the function is concave up. Okay, but it tells me that negative 1, negative 2 is a relative min. Okay? So this is kind of cool. I did have to take the derivative a second time, but I only had to plug in one number rather than plugging in 2 different ones and seeing if there was a sign change. Okay? So I'm going to do the same thing with f double prime of 0. And I actually get 0. So this fails, right? We'd have to use the first derivative test. However, because the second derivative is 0, what does that tell us about this point? What? This actually is a plateau point, and even more specifically, because second derivative is 0, it's a point of inflection. Point of inflection. The derivative's not undefined, it equals 0. If it were undefined, then we would definitely have to go back to the first derivative and figure out what's going on here. But this is a point of inflection. Okay. Now, this is just kind of a common thing here. If the first and second derivative are both 0, then you do have a plateau point. And that plateau point is also a point of inflection. Okay. So, all right, so now we plug in f double prime of 1, and we get negative 3, negative 3 plus 5. Oh wait, hang on. Sorry, I'm doing f prime. I was going to say, that sounded familiar. F double prime. There we go. So we're getting a negative 60 plus 30, which is a negative 30. All we really care about is the fact that that's negative. So that means that the 0.12 is a what? Relative max. Good. And guys, that's all there is to the second derivative test. Okay? Find your critical numbers, which you've already done, and then plug those into the second derivative, and that tells you whether or not it's a relative min or a relative max. Okay? Got it?
Yeah.
All right. And actually, if we look at the graph over here, you can actually see this happen. Okay? There's our relative minimum at negative 1, negative 2. Down here. 0 is not a min or a max. It's actually a point of inflection and a plateau point right here. But the relative max is right here at 1, 2. Okay? So there's our graph. And this is kind of the proof of what everything is. Okay? All right. Try this one on your own. Let's take a couple minutes. We'll try this one out. See how it goes. Okay? Okay, if you're totally stuck, I'll get you going here a little bit. Cosine of pi over 6.
That's not even a thing. I'm lost.
That's a thing. That's unit circle, right? Sine of pi over 6 is a half. Cosine is root 3 over 2.
Alright. We're good then.
Oh my. The sun pi over 2是啥来着？哎，怎么是3pi over 2啊？我算错了。啊？不应该是3 pi over 2吗？
Any of you frantically looking for a third value?
I'm hoping there's not one.
No, there just happens to be 33 columns in the table.
Oh my god.
Yes, Terry?
Is there any other variable points?
Nope, just 2. We just had an extra column in the table in case you mess up, I guess.
But why here have 3 boxes? I got it right, but here are 3 boxes.
We just wanted, if you messed up something, you could use the third one, I guess. Hey, be confident in your answers. You guys know, you know, there's only 2 angles where the sine is a half in from 0 to 2 pi. All right, so. All right, and if we do this, it's going to be pi over 6 minus root 3. Actually, I should say plus root 3. And this is pi over 6 minus root 3. It's the y coordinate. And guys, you can leave your y coordinates like that. Don't bother plugging it into the calculator.
Yeah.
Okay, so those are our 2 points. I'll give you a couple more minutes here to finish it off.
What's it up here?
All right, so what'd you get for your second derivative? What's the second derivative? Negative 2 cosine x.
Yeah.
Good.
Yay.
So what do I get when I plug pi over 6 into that?
Negative something.
Negative something. Yeah, we don't care what it is, but it's negative. That's good. And so that means that that point is a what?
Max.
It's a relative max. Good. Relative max. Because it's concave down at that critical value or critical point. We know it's a relative max. Okay? What do you get when you plug in 5 pi over 6? Positive something, yeah, because it's a -2 times a negative root 3 over 2. So the negative and negative is positive. So this is concave up, which you don't have to write in, but. So that means that that point is a. Very good, a relative minimum. Okay? Make sense?
Yeah.
Okay. So, this is the kind of thing that
Wait,
you'll need to be able to do.
When is there a point of inflection? When there is 0, 0?
The point of inflection would come where this equals 0. Okay?
So when it comes, when it goes down is max, when it go up is min.
Point of inflection.
So when it go down, it should be the max.
Yeah, think of it like it's concave down, so the point's sitting on top of that arch. Okay? When it's concave up, the point's sitting down in the bottom. So it's a min. Okay? The points of inflection here would be where cosine is 0, so that would be x equals pi over 2 and 3 pi over 2. And we could use our, we could then look at that, and look at intervals of concavity and so forth. Okay?